Слышно чего-нибудь? Раз, два, три.
Да,
Хорошо, ладно, сейчас я тогда
к
принесу.
сожалению, слышно.
Да, я принесу бумажечку, чтобы записывать. Ладно.
Это я как-то... Ай-яй-яй. Меня слышно, наверное. Ла-ла-ла. Share world. Yeah, while Vereshchagin seems not to be here, just I have a question for Bruno. So did you now know your proof of closeness of the cone. Does it finally work or not without quantify elimination?
Yeah, I've invented a proof, but it's not a short proof, and so I need to write it to see if it works.
If it's a complicated problem, don't worry.
It should be like one, yeah, but now I'm very scared.
What's the problem?
No, there's no problem. But Bruno called me and told me that he knows how to prove that the positive cone of finite set of vectors is closed. But then
Yeah.
it was not so simple as we thought initially, and there were some problems. And now to avoid this quantifier elimination, to avoid the Gauss elimination of variables, just give some kind of more abstract geometric proof, and it's what not obvious.
Yeah,
To avoid proving that it's a polyhedron.
No, it's not a polyhedron because it's convex. Any positive, it's cone. So you add any positive non-negative coefficients. For polyhedron, it's just a compact space because it's image of compact space under linear operation. If you have this octant, it's not compact.
No, I think it's a polytope. Well, I'm not. I mean,
no, it's a polytope, but how do you prove it without? How do you prove it without quantifier elimination? This is the problem. But okay, it's another story. Let's not mix this. Okay, so everyone is here who is known to be plans to come.
Maybe yes. Maybe
Yeah,
not.
Laran is here. Coeli is here. Bruno is here. Yeah. Other people do not tell me in advance that they will come, but no, Andrei is not here, but maybe he's busy. I don't know. It seems he was at some point.
Yeah,
here.
he was supposed to come.
Okay.
He told me he would.
Okay. Then let me check. Oops. No. But it's strange. Why cannot I? It's Zoom. Sorry. But
You wanna access to the board?
I tried to write something on the board stupidly, and I'm surprised why it didn't work. But you know.
Well, I can give it if you won't write anything. Okay. Chat.
Yeah. Okay. Good. It works.
Okay, so Andrei is not here yet, yeah?
Strange. But okay, maybe you can start slowly, and then if needed, repeat it fast when Andrei comes or something like this.
Yeah.
Sasha, maybe you can call Andrei on Skype or something, because it's very easy to forget about seminar.
Okay.
Yeah, okay, but I'll try to start anyway, but okay, the idea was to give two positive results, but they are not as positive as we would hope, but still that's something. And they're a little bit different. So like they are not quite as in the previous seminar where we showed, for example, that conjunctions are PAC learnable in polynomial time. So, okay, well, I'll try to state the theorem.
Алло, добрый день. Просто Саша Казачинский собирается начинать, так что если вы хотите...
Yeah, so...
Okay, so there's something happened there, so just he instructed to start. Yeah, sorry.
Yeah, so I'll try to state the theorem, assuming like more...
Which is positive, but not very positive, but still positive. Okay.
Yes, yes. Well, there has to be some introduction to the talk. Well, so here it is.
While Andrei, there should be an introduction. Yeah. Okay.
Yeah. So one theorem is about learning decision trees. So, and I want to state that decision trees are PAC learnable in quasi-polynomial time in some sense. But let's be more specific. So learning decision trees. So I guess everybody knows what's that. If no, then don't hesitate to
So you
tell.
just ask about one variable, then depending on the answer, you go along the tree and ask about another
Yes.
variable. And after some questions, you need to say what is the answer. So it's just an oracle computation.
Yes.
And you are
Something like that.
you care about size or about depth?
Yeah, I care about size. Because for depth, I guess. Okay. Yeah, so I care about size. So I want some algorithm. So what's the input of this algorithm? So I want to show that there exists a quasi-polynomial time algorithm which does something. And what is this? Its input. First,
So we have
receives,
n variables, and all the polynomial and quasi-polynomial are in the number of variables.
And okay, I will tell you what in size also the decision tree. So let's see. Okay, well, so the input is the number of variables first of all, and then some other parameter s. So we are, let's say, we are given the size of the decision tree, or maybe the upper bound of the size. And then we are also given like, I don't know, like a black box access to some pair T and D. So T, black box, I don't know how to call it better. So T is a decision tree on over n variables. Right.
So we have access not to the tree, but to the function it computes. Yeah.
Yeah, there is also distribution. So, well, so what I mean by that? So T is a decision tree over n variables of size n, of size s, and D is a distribution over the inputs. And so the algorithm is given not just is this pair in the following form. He can just sample an input according to D and get the value of T on it. So that's what I mean by the black box access to this pair. So is it clear?
So it's a bit strange. So it's really you are given just a sequence of examples. So you cannot influence somehow there is no real questions. They just provide a random unknown distributed inputs and outputs for them.
Yeah, let's say. So my algorithm can sample this independently according to D and get the values of T as many times as he wants. But of course, this will be like bounded by the running time of the algorithm. And if you want to sample exponentially many times from this black box, then you will need exponential time for that. So you have to care how many times you sample. So that's the input.
There could be a stronger, easier model for us. So then first we can sample D, and then second we can request the values of our predicate on any string, not the one which we sample. But this is much something more powerful. You just actually you have just what you have before in learning. You have just a sequence of values on random elements distributed over some distribution.
Yeah, let's say like that. I don't know. So in any way, so
that's clear.
We can have that we have actually an infinite sequence sampled, and then the algorithm.
I have a
can
question.
read
Do you obtain only inputs for the decision tree or the function value?
the function value, of course.
So
what I can ask,
it corresponds the basic model of PAC learning.
Yeah.
You
Yes.
just not specify the number of.
I just don't specify the number of samples.
Yeah, I see. Okay.
Yeah. No, it would be very special learning if you limit the input, but not to the values. Yeah.
Well, in the basic model, you don't have S upper bound on the size, but I think it doesn't matter. Probably you can get around this. So in 1984
S
paper,
means that we learn the decision tree of size at most test. It corresponds the basic model.
If
Well,
you
let's see.
don't
And
have
so,
a bound,
so
then this is just learning any function, so it's not possible.
no, the bound is allowed to depend on S. The runtime is allowed.
Yes, I understand.
And
This algorithm is not actually the learner from the basic definition, but now I see.
Yeah, but I think it's equivalent. If you don't know
Yeah.
S, you can somehow find a good S. So it doesn't matter. It's a detail anyway.
yeah, so
Output.
the output should be some decision tree, T prime or T hat, I don't know. And what we want is that, well, that it's close to our original decision tree. So if we take, for example, if we take a random example, then with high probability it will coincide with T.
And that's usually there are two probabilities. You once use the probability to coincide, which is a distance between t hat and t in terms of functions. And second is the probability to achieve this goal, which is the probability over randomized coins of this algorithm. Yeah.
Yeah. So, like our goal is to obtain some T hat such that, I don't know, I don't really want to be very specific about probabilities. Let's say my goal is to obtain T hat such that if I sample X, the probability that T differs from T hat is small. But my algorithm is in a sense randomized. Well, it's randomized that it receives random samples. So I require that to be also with some high probability. I require that.
You don't need your internal randomness. You just have the probability over the sample.
Yeah, but my output T hat will satisfy this property, I guess not always, but for most of the samples.
Yeah, that's clear.
So
but
it's
also you could allow internal randomness in the algorithm.
Internal randomness I could allow, but in that case I won't use it.
Yeah, good.
And so, yeah,
there exists general result that it's enough to have probability strictly less than 1/2. Like 0.49 is enough, even with delta equal to, even with very small probability over training set and randomness in the learner.
It's for decision trees.
No, in general, if you are PAC learnable,
No,
just
but
with the
here
fixed
the output
probability.
should be a decision tree.
but it's polynomial time.
Yeah, it's polynomial time. I wanted to explain it last time. It was in the last part of my note. It's boosting result. So if you have
But
it
here you have several decision trees, and most of them are correct. How do you combine them into one?
yeah, but it's not easy to explain.
But the result is for decision trees, yeah?
No, for
No.
any PAC learner.
No, but here the output is more specific. You have
No, the output, well, the algorithm takes in a set of classifiers and combines them into for every epsilon, accuracy at most epsilon with high probability and so on. But just, I tell this that what he does is perfectly okay. If we have a constant probability, it's good.
no, but what I'm saying here is something more than general PAC learning, because the output should be a decision tree, not just an algorithm. Still, it's true.
In this sense, he is stronger, yes.
But still, the general amplification is true.
Yeah.
Okay, we can believe it. And do we require that t hat should be of size at most s or not?
No. So the only thing is that our algorithm should works in time. Well, in time n to the O of log s. And in particular, only this gives us some bound on the size of t hat. But I mean, so like the philosophy here, or I don't know, that we don't necessarily want like decision tree of the same size, but we want a decision tree that learns our initial t well. And the only thing we want is that we wanted to obtain it fast. But unfortunately, like the algorithm doesn't quasi-polynomial time. And decision tree obtained is quasi-polynomial size. But at least it like learns t in the sense that it's close to t.
Yeah, but
in some sense, this also proper that assuming that I'm outputting a decision tree, that what you are saying also, not a circuit, let's say, or something, like not some stronger, more expressive way of representing Boolean function, just the decision tree also, but probably bigger size. So it's all, well, so there is some problems with terminology. So it's proper in some sense, but not proper in the other sense. So, but I hope that, I mean, so the statement is here. So I don't know.
But still, if you get an easier task, if you want to output a circuit, or if you just want to predict the answer. No, maybe it's not strongly easier, but at least it's easier.
I know an example where it's easier, but I don't know about decision trees. It's easier for DNFs. I mean, it's not, well, I mean, the algorithm is better if you're allowed to output, like, I don't know, circuit, well, actually like a polynomial there, but I will, I mean, I can tell it later, I guess.
Yeah, okay.
Because otherwise I would switch to completely different thing. So, and the plan is, okay, let's try to prove this theorem. If there are questions about the statement, then I can ask, but
Sasha, yeah. I misunderstood your question when I spoke about.
No, I thought that there may be an easier proof if we don't insist of t hat be a decision tree, but just as last time want to predict the value of t of x on a random sample from D in any way that is any polynomial way. But this could be theoretically, this could be easier. But I understood, Sasha, that it's not really.
I mean, I don't know. I mean, just don't know the results like that. Maybe they're obvious.
You
and I
don't know
just can't
any
think of
proof
them.
which would easy proof for this maybe weaker state.
Yeah,
Okay.
so, but I don't know. Maybe Bruno knows. But okay, let's try to prove it. So, and let's be accurate. So,
Good
as-
idea to to get this commitment in the beginning. Yeah.
yeah. So what I need is I need some procedure. But basically, so what I would do is so my algorithm receives a sample, and it just tries to quickly find some decision tree that agrees with all these samples. So the samples, I know the form x1, t of x1, xm, t of xm. And so m will be like the size of the sample. And I expecting that, so yeah, but there are good ways to do that and there are bad ways to do that. And we will, maybe somebody will come with a bad way at some point
Let me
that I
try
will now explain.
to come with a bad way. So we have
Yes.
different x1, xn. And so it would
Well, maybe
be,
they're the same.
okay, maybe they are the same, but then they can be eliminated. And so we
Yes.
want to find some.
To quickly find the decision tree which agrees with all the examples.
So we may try to find the decision tree which maps all the things in a different leaves. And then we can safely
Yes.
ascribe whatever we want to these leaves.
Yes, so you can just, indeed, you can just construct the decision tree. First, you have one leaf, I don't know. Like for x1, there will be specific leaf. So you come to x1, so you come to this leaf, and you read all the variables. And if they're like in x1.
Yeah.
So, okay, I mean, so first I try to, yeah, I'm trying to we just can construct a decision tree. So like initially I want just that the value of x1 is t of x1. So I just construct a decision tree which asks all variables. And then if it's x1, then I put t of x1. And if it goes some like deviates from x1, then I put whatever like zeros. And then now here comes x2, and it should be equal to t of x2. And then like I look where in this tree should x2 come, and then I read all the variables like x2, and I put t of x2 here.
And order on variables is always the same. Just
You can do it in any
Order
order.
on
I mean, you are trying to build a tree.
Okay, so like what I'm trying to do is that I'm trying to say that if I have a decision tree and then I have some input to it, and I want to make this input,
Yeah. So
this decision tree equal to something on this input.
yeah. So and then you try, and if it doesn't agree, you just add one more leaf.
Yeah, and the problem is that I also there is some how exactly to do that. I want to say that I can do this like in polynomial time, and but I don't want to spoil my previous examples.
Right.
So I want to maintain invariant that for any x1, x2, there is like a leaf such that on the path to this leaf, I read exactly all variables and they should agree with x1 with the corresponding sample. So that then when the new sample comes, I draw just a new leaf. So it could be that I just, so what I can try to do, I can try to, this means that if I change the tree, it means that in this way, if I have a separate leaf for each x, then I won't spoil it by changing tree somewhere else. I don't know
No,
if
but what
some,
you are saying
maybe
is
it's not.
completely strange. So what you can do, you can try you have a full binary tree in which you have some paths, and then
Well,
you
I mean, I don't want it to be full.
yeah, and then if after you draw all the paths, you can just if an entire thing is not needed, you just replace it by 1 0. So you just keep, you
Yeah.
don't need, it's not you really don't make, you can do it in any order. You prepare the paths one by one, but really what you finally do, you keep all the existing paths in the binary tree and compress the rest in a most trivial way.
Yeah, I mean, but your way is, well, you want to first construct the complete binary tree, and its size would be large. So, but I want
No,
like a
I
polynomial
construct it
time
only
in my,
mentally. No, I understand, but just the result is what I describe. Yeah.
yeah, more or less, yes.
Yeah.
But okay, I wanted to convince you that I can construct. So if I have like this sequence of examples, I can construct in polynomial time some decision tree which agrees with that simple sequence of examples.
Yeah,
right?
but the tree will grow as the number of examples grow.
Yeah, like
Very more or
the
less
main
linearly or something like that.
yes. So the main problem is that the size of the resulting tree depends on the number of examples.
Okay,
Sasha.
and then one can try to do something better.
Sasha,
Let me just say some stupid suggestions. So first of all, you can also try a tree which separates all the strings. So it doesn't take into account this T, but it just, we want to separate all the strings, but do it in a more clever way. Let's look at the strings and take variable which is most informative about this. So it split the strings into groups of most best possible way in terms of proportions. And then you can do the same for each group, finding another variable which split them in the best proportions. And then you get some economy. Does it?
But Sasha, this makes some economy of depth, but not size. I mean, the size of the tree obtained in Sasha's constructions is anyway about 2m or close to m. So your economy just economize the depth.
Still we need separate vertices for every x. So we cannot do much better.
Well, we will do something like that, but we'll have to take into account the size.
But Sasha, the size is in our control. We can use any m we want. So I don't understand actually.
No, if we just take very few values, then there's very small hope that we get a correct or a useful tree.
Sure. So maybe we should start with understanding what m we need.
No.
Okay, but let me say a second stupid thing before you say something clever. So the second stupid thing, you can consider this t function with x1, xm. And then you can try to find out which of the variables has most influence on the value of t. And then ask this variable first. In the worst case,
Sasha,
you need to use some Fourier analysis.
Like that. No, Fourier analysis, I don't know.
You don't need Fourier analysis. That's good news.
I don't need Fourier analysis. But there will be something, it will be very simple, but you just need to accurately say everything.
Okay.
No Fourier analysis, no, just
transfinite induction or infinite injury priority argument, that's all good news.
No. However, but this is actually Ehrenfreud and Hausler, but though the theorem. So in its 80s, so I forgot to say. But
okay.
It could be something like that, but it's not. But
the same
okay, the lemma what we need.
By the way, if you started to say the name. There is
What?
Ehrenfeucht for a game about elementary equivalence. It's the same Ehrenfeucht or different one?
Well, I guess the same. I mean, like the famous.
Ehrenfeucht is the same, but the result is different.
Yes,
that's I even
exactly.
started to think about this difference. Yeah. Good.
Yes. So what we need is, so we need the following algorithm. So it obtains examples, and it also obtains the parameter s, well, and n. The number of variables, and it outputs, and the promise that they come from a decision tree of size come from
Size S, I guess.
a decision tree of size at most s. And then the output should be decision tree. Decision tree. And its size should be a t hat which agrees. Well, I mean, let's write which agrees with examples. And its size should be n to the O of log s, but not depending on the number of examples. But the running time will be, I don't know, the running time will, of course, should depend on the number of examples, but it will be something like polynomial in m times, again, this n of O of log s.
But what you claim that you can do it for very few examples or for very large number of examples, because if we have few examples, the task is simple, and if we have a lot of examples, then we have a lot of information about the tree, and so we can do something. Yeah.
Yeah, maybe. So I claim what I claim. So the one thing is to try to understand why is this sufficient for learning, and why, and in this thing it's important where this comes this condition that the size of the tree shouldn't depend on m. So let's try to understand why this lemma is sufficient. Why the lemma is sufficient?
So the problem is that, okay, we have find something which is consistent with existing examples, but in general, this doesn't immediately say why it will be good for a future example. And now you will explain that it's enough.
But let's consider the set. Okay, but we know that what we have outputted has size n of the, it must n to the O of log s.
And number
so we
of
always
decisions. So number of
so
decisions of size k is at most n plus 2 to the power k. So we know that if we output classifier from small set, then it is okay. I explained this last time.
So you say that this was already explained last time, so we now repeat the explanation, yeah, or what?
Yeah, because
I mean the slight difference is that this set is larger than, like, so you have classifiers, but your output in something which is in a superset, the classifier, which is still small.
Yeah.
but I guess
Okay, but this nice picture of a potato with things inside, it symbolizes what?
it symbolizes okay, yeah, I guess it symbolizes a set of decision trees which we can output.
Okay.
Sasha,
And
it has exponentially many decision trees, right?
yes, it has something like 2 to the n of log s decision trees. But we discussed last time, so if we have we discussed last time that if we have an like a set of classifiers of size s, we need log s samples, and if we just find a consistent example, a consistent classifier after order log s samples, then this classifier with high probability will be good. So it will be close by the distribution to the real objective function from where we drawn the examples.
So this argument goes that for every wrong one, we have some bad set, and since we can, if we have a big sample random, then we can treat any element of the sample as a test question, and all others as a training set. And if we are not successful, this will mean that we get in a bad set too many times, and Chernoff bound doesn't like this, and so on. Yeah.
Yeah. So I mean, okay, I can say it just quickly one of the ways. So if I take any decision tree from here, and I'm interested, like, and I'm drawing in examples from T, which is fixed here but unknown NT. Then first there is like the distance between this tree here and T, which is the probability that for an example drawn from X they differ. And on average, like if I take a sample, many samples, the number of samples that disagrees with T will be this distance between this. If it's some T1 and the probability that T is not equal to T1. So on average, then a sample will disagree with T1 with that probability. And then by the Chernoff bound, if I take M samples with some probability exponential in M, for T1, like the fraction of samples where it differs from T will be close to that probability. But then if I take M of order N of O of log S, then this should be minus. Then this probability that like the fraction of samples where we are different, and the difference between and the real distance to T or according to D, so it will be very small, that these two quantities will be far apart. It will be exponentially small. And then by the union bound, it will hold for all decision trees in my potato. It means that if I output any, then with high probability, if I have a decision tree which agrees with T on all the samples, then the probability that T differs from that T hat should be also very small, should be close to 0.
Yeah, so if some output decision tree is close to the real one, then there is no harm of outputting it. If it's far from a given from a given one, then this is a serious problem. But for each output decision tree in our family, which is far from the given one, there is
it's very unlikely.
overwhelming probability that it will not be chosen because it won't be consistent even with the training set. And we choose something which is consistent with the training set. And why will not be chosen? Because if there is significant part when they differ, then with high probability we will get into this part. And don't even need Chernoff bound. It's just probability bounded. Why do we need Chernoff bounds? As I'm lost now.
To show that.
If you are at least once in an error set, then you cannot choose this output decision tree.
Okay, so you're saying that if decision tree, like if this probability that T1 differs from T is large, that it's bigger than 0.9, then it's obvious then the probability that we get a sample which agrees with T1 and T is like 0.9.
So the probability to be something
M.
which is 0.9 to M.
Yeah, I agree. And you take M so that this is sufficiently small so that these probabilities, if you sum up over these potatoes, will sum up to something smaller than 1.
Yeah, of course, we have many possible wrong outputs, and if we take, if we consider all the possible functions of all the decisions tree of unlimited size, then of course we fail because we have too many of them. But here we bounded the output size somehow, and so the same to beat this thing, we need the same kind of M. Yeah.
Yes. So now our task is to prove
let's now stop and ask: is it clear or not?
It is.
It is, but maybe someone else can confirm this.
Maybe.
Yeah, are there such exceptional people? If there is less than 1% of them, we can try some people randomly and then see if there are many of them. We should succeed.
Pick someone at random because.
No, Georgi, for example, it's not completely random, but I want to maximize the probability. No?
Well, I think I get the main idea.
No, but really there is not much beyond the main idea. Here it's just the argument is quite no, one needs to understand the setting. So there is some mistake. We assume that there is some argument that finds a decision tree which is not much bigger, but which is consistent with all the examples.
Yeah, and the size is independent of the number of
log s. And then no, if it will be 2 and O of log s, it will be polynomial in s. But then it's somehow bigger than polynomial in s. It's log s times 2 to the log s log n. So it's bigger. But still it's not much bigger. So the claim is here in this argument is that every algorithm which provides a circuit which is consistent with existing example is also good for prediction. The circuits which it provides with high probability will be 90% close to the correct one.
Decision tree, I guess you want to say.
Yeah, decision tree, which is predicted, is with probability 90%, will be close to the true one. Georgi, so is it clear? Just say something, whether it's clear or not.
Well, yes, I think it's
It's
mostly
everything is
clear.
confusing, or
Not really.
okay. So if it's so the question is that the probability of failure of our algorithm. So failure is just it predicts some circuit which is far from a real one. And this failure we classify into different types of failure. One is predicts the specific circuit which is far from the real one. And the number of possible types of failure is bounded because the circuits which it predicts are not too big and not too much of them.
Decision trees.
Decision tree. And to have a failure of specific type, we need that we need that our sample is always, for strange reasons, is always in the part of the space when our wrong circuit coincides with the right one. And by assumption, it happens in more than 10% of cases.
Mm-hmm.
So we should avoid this set
many times.
And so it's 0.9 probability to avoid it in one step to the number of.
Yeah.
Not convincing.
But
No,
it's
no.
in the note.
Yeah, it sounds like a standard proof of such things.
Yeah,
where we
everything sounds like that. The question is,
we have some really
you cannot distinguish a standard, a trivial lemma for wrong lemma. This is the main problem of mathematics. Yeah. Okay.
Yeah. Okay. So now
but
let's try to.
We don't know how to construct this circuit, so we just know that it's enough to construct. So the lemma is sufficient, but we haven't proved it.
Yeah. So let's prove the lemma. So what's the idea? The idea is to try. Well, I mean, okay. So what stupid thing we can do? We can try to just search for all decision trees of size S and see. It's like very stupid brute force, and then it would be good learning algorithm as we shown, but there will be even no overhead in the size. But of course, the problem is that then it's exponential. You need to find exponential time this brute force. So the idea is to do a more clever brute force, and the more clever brute force comes from the following observation. So if you have a decision tree of size S, you have a function computed by decision tree of size S. It means that in that decision tree of size S, there is some variable which is asked first. There's some xi. And then there are two subtrees. So there is one so then there is one subfunction. So you have this function, and there is a subfunction where you fix xy to 1, and when you fix xy to 0. There are two subfunctions. And one of them has size at most S over 2. Right? You have a decision tree, the size, I mean the number of leaves, one of the trees has the number of S of 2. At most S of 2 leaves. So what you can do? So you can, but the problem is that you don't know this variable. So we can try all variables. So what we can try? We know, so we are given that our example is consistent with.
So imagine that one of them, if both of them were small, we could apply recursion. But if one of them is small, how does it help?
But still, the other at least has one less variable.
So we will use a more smart recursion. The recursion will involve the number of variables and the size.
Yes. So the idea is that we try all variables. And so we are given that our example comes from decision tree of size at most S. We know that if there is a way of fixing one of the variables such that there are 2n ways of fixing a variable.
And it's
to 0 or to 1. Yeah. And we try all these 2n ways. In search of some subfunction, and we try now to find a decision tree of size at most s over 2 for that fixing. Maybe we will fail. Well, then I have to accurately now, okay, what does it mean fail? We will, like, maybe our algorithm won't give any output because it maybe actually this is a wrong it's a wrong subfunction.
We assume that the size of the tree is small, but this assumption was wrong. So we will
wrong. So our algorithm might say, okay, you know, I don't know what to do in this case, but at least once we will succeed. But the point is that we do that 2n times, but still we do that with s being halved. And but then, okay, once we found any variable x size, such as, let's say, if you fix it to 0, the size is halved. Then what we do, we just trying to find a decision tree for the other subfunction. Now, just with the same parameter s. Because we cannot say anything good about the other sub. Well, the only thing we can say that this subfunction has one less variable, but about its size, we cannot really say something, because if this is really small, then it can be really close to s.
But we know.
But the point is that
most s. It's enough.
Yeah, but I know that the size of this subfunction, when I go to the subfunctions can have only they cannot have bigger size than the original
but
superfunction.
Even s minus 1, Sasha.
Hmm?
Even s minus 1. You can replace here s by s minus 1, right?
No, I don't replace it by s minus 1.
But you could.
If you want, but you don't want.
Well, I mean, I can do probably, but that won't really help, because, I mean, there is another parameter which decreases by 1, it's n minus 1.
Okay.
So you get either s over 2 and n, or s and n minus 1.
S over 2 and n minus 1, I guess it's better. To always ensure that at least the number of variables.
Sasha, when you find a right variable and the right value, you repeat the algorithm to the second sum function, right? For the second sub function.
Yeah. So when I find a subfunction such that my algorithm succeeds with s over 2, I just take the other subfunction, but run it with s, maybe if s was minus 1 if you want, but I don't know, won't really help, I guess. But also with one less variable. So, but this thing, when you do not decrease s, happens just once. So this is because and this is why the algorithm won't be exponential and just quasi-polynomial.
So what do you mean by happens once?
Well, okay, so there will be like a recursion. 2n times we run the algorithm with parameter s over 2. And since we decrease it by half, this like, so, okay, so this will give us a quasi-polynomial time, but at least not exponential, because
yeah. So just let me try to write a recursive statement. Is bounded by 2n times t to the n minus 1 s plus t
over 2
over s n of s over 2. I just want to.
No, it's wrong.
Sasha, you're not right. You're not right. 2n
The whole point is just, yeah, to n.
See, n over s over 2, I guess.
Yes.
First of all, you try all the sub-functions to n, right? To n sub-functions.
Yes.
And for each, you apply your algorithm with the second parameter halved, right?
Yeah.
And then only once you have found.
So you
variable,
say that you want to write
then only then.
to n times this.
I think this is the right recursion.
Yes. Yes. And its solution is
I don't
quasi-polynomial.
understand, but our first try may be incorrect, and we should apply this second.
And this, Misha, this is because we multiply this by 2n. We make 2n trials, consecutive trials.
But before we try our second thing only after we find something for the good direction.
Yes, but how many times we should do it?
2n.
The second times the first thing, trying all the substitutions, we do 2n times. But until we find a good one, we did not start another part. And after we find a good one, then we substitute everything for.
But what we shall do if this second part fails?
No, it cannot
But
fail.
it won't fail.
If our original circuit has if original function set of example have a decision tree of size s, then of course the new one also will have. But by the way, I don't like.
I don't understand.
By the way,
it is possible that we choose a wrong variable for the first branching, and then we can fail at the second.
S-1. But even if we fix a wrong variable, the decision size cannot increase. The decision tree size of decision tree cannot increase if we fix a wrong variable.
I see. I see. Yes,
anyway.
You are right. You just insert the whole unknown decision tree to this. Yeah, agree.
Yeah, but Sasha is writing something which is probably not a good idea because we missed this. Okay, what you are writing?
Yeah, I will. So let's try to say it all once a bit more accurately. So what we actually need. We actually need a procedure where we have some with the following.
N is a number of variables. S is a number of
it's a parameter, and
the third.
And now we get a training set. And the point is that in my algorithm, there is some moments where this training set cannot be satisfied by a decision tree of size at most s, right? So I need to accurately say what this procedure should do in this case. So, what are requirements? So the requirements are, so this procedure can either output a decision tree or say failure. But if there exists a decision tree of size at most s which agrees, then no failure. It cannot output failure.
No failure, but it can output a bigger decision tree.
Yes.
Okay.
But the point is that now the second requirement is that if it outputs a decision tree, even if sometimes it may output a decision tree even when the size of when training set cannot be satisfied by a decision tree of size s. Sometimes in these cases it can output failure, and sometimes it can it can happen that our algorithm doesn't notice it and it outputs some decision tree, but it always has to be of bounded size. About a decision tree, then
So when it outputs something, it's a decision tree of correct side that satisfies is consistent with the examples. And this can happen even in cases when the original tree doesn't exist. But at least in all these cases, it should work.
Yes, and we see that this thing. So now, how this procedure work? Again, it goes through all 2n variables, and now tries to run all 2n sum functions and tries to run on them with s over 2, with half less s. And if it doesn't succeed, so it means that our initial training set couldn't be satisfied by small decision tree, right? Because if it could, then we would succeed. It means that in this case, we can safely output failure. Now, if at least once it succeeded for one subfunction, then again, we try for another subfunction, we try to find this, to run our procedure with s, again, with the same s. And again, if our promise was satisfied, then we will succeed, right? But now we only have to show that. So the only way we output something if we succeeded at least once on these 2n subfunctions and succeeded like the next time where we try our procedure with the same s on the other subfunction. And then, so we output something only when both of these things, and then we combine these two things. But then what we combine has size at most an minus s over 2 plus an minus 1 s, right? So we obtain the following recursion. And its solution is quasi, well, I mean, even that recursion has a quasi-polynomial solution. But that also, but it's smaller, but it's still
not quite obvious
quasi-polynomial.
why the previous recursion is quasi-polynomial.
So no, I don't know. So you improve something according to the previous recursion recurrent formula.
The previous recursion is for the running time. This recursion is for the size of the tree that I'm outputting. And it's smaller. It's better recursion because you don't have to just bind it by the running time. You now
you don't need
just
multiply to n because you just take one, which is good.
Yeah.
Do you claim that the running time is also quasi-polynomial?
Yeah, I think I can try to explain this. So what do we happening? Let me try to I made some computation meanwhile. So we have initially we have 2n possibilities. And for each of these 2n possibilities, we also make 2n possibilities recursively for s over 2. And this is done for log s steps. So in this way, we get 2n to the log s leaves.
Yeah.
But also, so imagine that we are happy and we can, in this way, we can find some path which goes to this tree successfully. So every time there is one correct choice, and we make this choice. And after this choice is made, you can then apply this argument to the remaining function. So you also need to construct all the long functions which have n-1 variables and s. So you have 2n times 2n to the log s times plus.
I don't understand why the depth of the tree is log s. I think
Because now we consider only the tree of choosing the simple part. No, it's not full tree. It's just the tree when we are looking for the simple part.
Actually, on the second step, we should repeat this recursion construction. So you implicitly insert in this tree many other subtrees
on the second,
corresponding to less number of variables.
But the first construction. Okay, so what is, we should multiply it by something, yeah?
Yes.
So we should multiply but by t of n-1 s, yeah? Or something like this.
Okay.
So is it correct or not? So
this inequality seems to be correct. But it's not quasi-polynomial as I see.
Yeah, it's not quasi-polynomial, obviously, and it's bad.
Yeah. So I'm doing some, okay. Then I'm doing something stupid. Yeah. Sorry for that. Okay, so maybe so there is another obstacle, not strange thing, somehow kind of paradox. So you construct a decision. So there is one. If we have a decision tree, then fixing one of the variable will decrease the size of decision tree at most twice. But in our, we don't care how much examples from our training set go into this decision tree. Maybe there is a good variable, and indeed it has a small decision. If y is equal to 0, then the decision tree is small. But maybe our distribution is skewed, and we don't have serious, just have no examples with xy is 0. Isn't it a problem? So somehow there are two divisions on variables. One of the is defined by the decision size.
Sasha, it's not a problem at all. If there are no examples where xy is 0, then we obtain 0 such examples. So we go to the left and we decrease the number of variables.
So we get a simple decision tree because we don't have any examples. Any decision tree works. And then we don't care whether it's completely different from
the
real decision tree.
Yeah,
I can solve the recursive relation and prove it's quasi-polynomial.
Very good.
So, but the recursion relation is just let's erase everything.
I would be grateful if someone explain how to solve this.
So this is not needed, I guess. Yeah.
No, just a relation of T and S, and I can solve it.
And then you can solve it. Yeah.
Actually, we have a lot of other pages in Jamboard. Why do you need to?
No, we do not need to erase, guys.
Okay. Sorry.
Who is erasing?
It's me who is erasing because I don't like.
but I mean, okay, one way I was just to check that with some constant. If T of n, like you're proving an upper bound by induction, that T of n and s is bound by n to the c of log s.
So you want to check, not to explain the size of the tree, but just to check it somehow formally.
Yeah.
Okay, if you insist, let's do this. Okay, let's go to the next page then.
I think I know the proof without any recursion that the tree is small.
Okay, let me please check that I will copy this on the next page, and you will and make space there. And you
Well, I
will,
guess you can also try to say that you can describe like
Sasha, I do not need actually space.
okay. Okay,
So
then I will not write.
I do not need any whiteboard to explain what happens. So
Okay.
we have constructed some tree, right? Decision tree. So on each leaf, on each path in the tree, we ask some variable. And let's say that the variable, I mean the step down on the tree is good if that variable corresponds to the right choice.
What do you
Then
mean by right choice?
right choice when the value of the variables halves the size of the tree, right?
Yeah.
we are talking about recursion tree or about the decision tree?
About the decision tree. Let's look at the decision tree we obtained, right?
Yes.
And I guess that path in that tree correspond to the value of the variables, we know, right? And there are good values and bad values. In any path, we for sure have at most n variables, I mean, in every path. And in every path, we have at most log s good variables, right?
No, not necessarily. Other variables can be also good, but we just don't use this in the argument. I don't understand.
What I want to say that the number of paths is at most the number of strings of length n, binary strings of length n, where the number of good values is at most log s. Maybe I'm incorrect because that's a bit intuitive.
Okay, but do you claim that you use something except the recursion, the bound?
I don't need the bound actually. I thought that I have a proof without any recursion. But let me think.
But you cannot apply it just to the bound to prove that this bound is quasi-polynomial.
Okay, forget.
But it's easy to see that's quasi-polynomial because if you replace, let's say L equals logarithm of S, and then let's look to the relation for A. Then we recognize binomial sum of binomial coefficients.
Yes, but it's for A. For
Yeah,
A,
for
it's
A.
obvious. For T,
The question is about T.
Okay, but then it's also easy because let us assume T is bigger than, okay, so let us now say that L is equal to so let us rescale so that we have L minus 2 when we divide S over 2. And then we can just think that T is bigger than n to the power log S, n to the power L. And so we can gain minus 1 by just, if we go from from L minus 2 to L minus 1, we can believe it grows at least by 2n.
No,
so it's just a technical
do you
step.
derive this from this inequality also only?
Yeah, also,
the
yeah.
Then
yeah.
Can you do it on a new page?
no, Sasha, can I explain it? Just try to explain it like without without white.
And using only inequality.
Yeah, you're only using inequality. So
Yeah.
we have to show that there are just a few nodes in this recursion tree. And I will just show that I can describe each of them by like a string of size log n times log s.
Yeah.
And then, okay, so any decision tree, any node, you have to describe a path to it. How you can describe a path to it? Well, it consists, you can choose like, in any step, you can choose one of these 2n, I don't know, simple, like 2n options, or you can choose one option to go on the hard, 2n simple options or one hard option. But then this path, you can, how you can decompose it. You can decompose it like you say that, okay, at some point I choose one of the 2n simple options, and then for some number of times I choose hard options. And then again, I choose a simple option, and then for some number of times I choose the hard options. But each of these steps, you need log n bits to describe. You first describe which simple option you choose, and then how many times you choose the hard option. That may be 0 or 1 actually, but still, like, I decompose everything into, but then each time I choose a simple version, everything is s is halved. So then this number of like this.
I'm sorry, but I don't understand. Simple options divide the path into several parts, and you should specify the length of the paths. How
So let's just make encoding argument. So encoding argument. So we have a path on this recursion tree for this specifically for this not anything related to decision tree. We just take the recursion path in this tree for t and an equation. So there is 2n plus 1 options, 2n options of the first type, and 1 option for the second type. So we use encoding. So for the option of the second type, we use 2 bits. And for the encoding option of the first type, we use 2 log 2n bits. To encode,
No,
there we go.
Not right.
No?
Because you cannot say you use 2 bits for the second option.
Why?
Because you should specify a variable.
You should partition all this. So all the path into the following steps of the following form. Where you first choose a simple options, and then for some number of times you choose a hard option. Because you want to decompose your description into at most log s parts, each of them having at most log n bits. And to do that, I'm suggesting the following. You take all the places in your path to this node where you chose a simple branch where you halve s by 2, where you halve s. And there are at most log s of them. And then to describe what happens between two consecutive branches, like simple branchings, you just need to specify the number of times you chose the hard option. But when you choose a hard option, you at least increase the number of variables. So when you chose the hard options, you can do this at most n times. So this is also some log n bit number. So for any chunk, for any like part between 2 simple options, it can be described by log n bits. You need to describe which simple option out of 2n you chose, and also how many times you then went through a hard, how many times you use the hard option until the next simple option.
But I'm lost. Why cannot I use just the prefix encoding for all the choices?
Well, I mean, then if you just never use the simple option, then you will use 2n bits.
Ah.
And how you avoid this problem? I don't understand actually.
Well, for example, in that case, I use log n bits and not to n bits.
Ah, I see. Actually, yeah, I see. You consider all variants to partite a recursion path into simple steps and ordinary steps. And actually,
Yes.
the number
So
of
there's
simple
like
steps is at most log s, but we don't care
Yes.
because each behavior between simple steps is just the number of this. Yeah, okay, I see. So we have at most the length of recursion path is at most log s plus 1 times log n, but plus 1 does not matter. Okay.
Yeah, but
Yeah.
probably I don't
So,
understand.
yeah.
Yeah, I understand what you are saying now, but now I have a completely idiotic question. So we somehow have bounds for the number of vertices in the decision and in the recursion tree, and
Yeah.
and
So what is your idiotic question?
how we derive the inequality for that? So we just have
Well,
T
I mean,
minus. So we assume
Well-
that T minus is just the number of paths in a tree.
Yes.
Actually, the proof Sasha explained is not based on this inequality, but it seems that it can be adjusted to prove this this recursion.
No, I think Sasha claims that this argument applied to every function t that satisfies the inequality. No.
Yeah. I mean,
Oh,
okay.
I see.
I just directly
Yeah.
argue about the recursion
We
tree,
can see the
but if you
recursion
can take,
exactly for this inequality. Okay,
yeah.
I'm happy now.
So I'm arguing directly about recursion tree, but then if you have just this inequality, you can, I don't know, you can take a tree
And compare the t with the number.
I see.
that corresponds to this Tn of S, and then argue about this tree.
Yeah, no difference at all. Okay.
So and so in this way you can, well, if you have any polynomial instead of 2n, then it's the same. So yeah. So I have like 5 minutes, so I can say at least what we know about DNFs in that case.
Yeah,
So
yeah.
DNFs.
But what we already proven. We proven that you can learn in this
Decision
time,
trees and quasi-polynomial
you
time.
can learn decision trees in quasi-polynomial time and even produce some quasi-polynomial tree, not just trying to predict something, but just you predict it using a tree. Maybe big.
Yeah. And so for DNFs, the situation is follows. Well, I try to say, so we can learn DNFs in time t of square root of n log n.
So n is a number of variables.
And t, so log s here, but the number of variables is n.
N log.
And
S is the size of DNF and n is the number of variables.
yeah, s is the number of terms, let's say. And the idea is like the same. So we are trying. So we are trying to fix one of the variables such that the number of terms decreases.
So what is
now
term?
the problem.
What do you call term?
So DNF
I
is a
don't know.
disjunction
In
of
Russian,
several
it
conjunctions.
называется conjunction.
The number of conjunctions in a DNF.
Clause.
Okay, close. Yeah, but close up for
DNF, not CNF, but okay.
So again, we are trying to fix, but now the problem is that I cannot say that I have a fixation which halves the number of clauses. Well, what can I say is only that if I have S clauses, right? So if I have S clauses, and in general, each clause can have up to n variables. and there are also like literals, right? There can be some negated, right? So actually they're like, but what the only thing I can say is that there is a literal which appears in at least S over 2n terms. So if I'll fix it in some way, this fixation will just decrease the number of terms by factor 1 over 2n. Right?
Right.
And so inside of the size of the decision tree, you consider just the total size of DNF count with the sum of the
sorry.
number.
Yeah. Sorry, I stated a stupid thing. I mean, yes. The problem is that, well, I mean, if I have a clause which has a lot of variables, that's good. But in general, I'm imagining that I have okay,
No,
yeah. So I have.
If you want to say some simple things, so all the variables are either x1, x2, x3, or so we have n variables. So one of them occupies 1/n. So if we fix it, we get something which is 1 minus 1 over n even. Why you do such a strange? Why you need
What?
no,
Why I need 2n?
Some literals. And of course, one of the variables appears in 1/n of all literals. So if we fix it, we delete this, either this variable or the entire clause.
Yeah, okay, yeah, even better.
Why do
but
we
still it's better.
Complicated things.
But wait, what do we want? We want to construct a decision tree for that DNF.
A DNF. Well,
not a decision tree, a DNF.
Yeah.
Yeah. But the problem is that if this will be better if I decrease just a factor of this, then I will get like something not 2 to the O of n, not 2 to the square root of n.
So this is not
the main idea
for the reduction, for the induction, yeah.
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 The idea is that to separate, so we will is to treat separately clauses of size larger than square root of n and smaller than square root of n. So the first step is to get rid of all terms that are larger than square root of, have more than square root of n variables. So now the first step we will just care on the number of these terms. And for them, it's good that this term has at least square root of n variables. It means that there is a variable which appears in one of the square root of n fraction of these large clauses. And now, like the factor will be like that, and so we will get rid of all of these clauses in 2 to the square root of n log s steps. But now when we have all clauses that are of size at most square root of n, we can do the same thing as we did in the previous seminar. We just can, now there are like, the number of clauses is more or less 2 to the square root of n. And then you can just, so it's basically, you can replace everything to a problem of searching a disjunction in this larger dimensional space of size 2 square root of n. So you just try to find a disjunction consisting of like this is now a square root of n DNF. And there are like about n square root of n terms, possible clauses. And if you just go through all possible clauses and you see which of them do not contradict any of the examples. And then you take a disjunction of it, and it should agree with all examples. But this will be time like n to the square root of n, just because now we got rid of all the clauses of the big terms of all the big clauses. So that's the idea how you get a learning algorithm for DNF, which is square root of n. And just very simple, and I was very quickly that we can actually now there is a result that shows if you are allowed not to output a DNF, but a circuit, then you can get better, faster algorithm which works in time to the n to the 2/3.
So if you need just a prediction, then it's easier somehow.
Yeah, if you don't have to output a DNF. And they like how's the result proof? You show
Sasha,
that
wait a second. And what is our input?
our input is a training set which is let's say which is supposed to agree with some polynomial size DNF.
Okay.
And then is the number of variables.
Mm-hmm.
And I'm claiming that I have a if I can output not a DNF but something else, I have a faster running time. And the idea of that algorithm is that I will show that every DNF of polynomial size can be like computed by a polynomial of degree n square root of 1/3. And then instead of just DNFs, I try to find a polynomial, well, I mean the sign of the polynomial which agrees with all the training set. And output any polynomial which agrees. And now see, like, and polynomials, they are like infinite family, but they have BC dimension and like their degree, more or less.
Wow. Does anyone understand this? Or maybe knew this argument before?
No.
No, I mean, yeah, I mean,
It's too fast to me.
I don't know how to go from DNF to polynomials.
Okay, so then the question is whether we want to hear this argument, because of course it's more complicated the first part, and even the first part was difficult for us. So the question.
well, I don't know. I don't know how exactly this part that you can compute any DNF by small degree polynomial works. I have to read it, but well, I mean, this thing is just some separate statement not related to learning, which implies learning in some sense. But the learning part is just easy. I mean, I'm just showing that sometimes it's possible that you obtain something better if you're allowed not to output a DNF. And the idea is that basically instead of DNF, you consider a larger class which is PAC learnable, but in polynomial time.
So there is a larger class which is PAC learnable, and that contains all the DNFs. Yeah.
Yeah. But
so what
now
is
the
this
class
larger
is like
class?
the class of all polynomials of the multivariate polynomials of degree n to the 1/3. More precisely, their signs like positive, negative. Okay.
And arbitrary coefficients. Real.
Yeah. Yeah.
And this class is PAC learnable.
Yeah. In time, more or less log of the size. And for that, you need now the theory of VC dimension, unfortunately, because not just its size is small, but the VC dimension is small. Like, more or less, you have how many degrees of freedom you have, like the number of coefficients, which is 2 to the O of n 1/3. But now you consider real polynomials, so you cannot just say that there are like a few polynomials. Now you have to say that you have small number of degrees of freedom, yeah, and use VC dimension theory to say that if you just find a polynomial which agrees with your sample training set, then it learns good. If you use like the number of samples will be the number of degrees of freedom that you the VC dimension.
This is very advanced blah blah blah. So you need to explain it in more detail. But I have a very stupid question. So it seems that there is some natural. Imagine you have a set of samples, and you want to construct a DNF which is consistent with them. Then you just look which variable looks most correlated with the result of your training set. So which variable gives a better separation of the probability of success between the yes and no answer or something. What gives it more information about the value of a function? And then after you choose this variable, it's natural to ask it first in a stupid like in the games for how to guess something or how to weight something. You take the first weighting, which decreases the entropy in a maximal way. It seems that you can try to do this for learning also. And then if you try this variable, then you can apply the fixed two values and then apply everything to the rest of these things. Is it completely stupid and doesn't work? And we need some strange complicated procedure instead? Or it works also, but you need to prove it?
Well, it's a good way. It's a natural thing, but the point is that you have to relate it somehow to the initial assumptions that your DNF, that your training set comes from a small DNF. And in that procedure, you don't take this into account at all.
Yeah, but okay, but just yes or no question. Is this procedure correct or not?
That is the case that it's balanced.
Yes, I guess.
I guess it can be balanced for all of the variables, like for XOR, but XOR doesn't have small DNF. But maybe there is another strange function for which for every variable is
so
balanced.
every fixation of the variable doesn't change anything.
Yeah, I think so. No, I don't know. But
of course, it can happen if it's a function like parity. Then asking any variable doesn't help you at any way.
Yeah, that's what I want to say.
But
maybe,
of course, you need to use somehow that if the tree is small, this cannot happen, or something like this.
Why shouldn't it not happen? That's strange.
Okay, so just my request is to comment on this two stupid idea. First stupid idea is about decision tree, and the second stupid idea about this DNFs. So somehow, if we have a function which has some small simple Fourier representation, then we can just use this approximation, taking some finitely many Fourier coefficients.
Well, okay, I don't know, but what's the learning out? How you can you choose? You have a training set, and then you choose the variable such that what?
No, I using the training set. Yeah, I use this training set because it's kind of a more Monte Carlo training set to compute the Fourier, to estimate the Fourier coefficients, and then I let all of them which are small, we just ignore them, and then we keep what is big and use it for approximate value and
how
use it for prediction.
Estimate Fourier coefficients by samples.
Fourier coefficients come from uniform distribution, and there is some other distribution.
Okay, but for at least for uniform distribution, it's working or not?
Well, then continue. You when if it's a uniform distribution, you're trying to approximate Fourier coefficients.
I try to approximately find the Fourier coefficients, and that let only few of them which are big, and use this few things for prediction.
Ah, so you just
is it a completely idiotic thing, or there is something in it?
Well, I'm not an expert in Fourier
In what way
analysis, but
you
I mean,
approximate Fourier coefficient? What is your formula?
well,
I just take average
the
of
Fourier
sample
coefficient
instead
is
of the
some
integral.
expectation of the product of our function with some
So you
orthogonal
you
basis.
just use this arithmetic mean for samples.
Yeah, like
I'm just
in
doing
Monte
the
Carlo.
stupid thing which comes to mind.
I don't know, but it seems that it does not work. You need something more complicated. I'm not an expert, but in this simple way, I doubt that it would work.
Okay. So this is
Actually, the idea is very simple. You have some probability to large deviation in approximating of Fourier coefficient. There are a lot of them. So with high probability, you fail in many coefficients. And your choice of the heaviest Fourier coefficients may be corrupted in this way. It's a simple explanation. Maybe it's wrong. I don't know.
Yeah.
To me, it's not a simple
coefficients?
task to check
Well,
your.
to do the same. Well, it's not a
conjecture.
problem. There are many of them because you can have many samples, and then there will be exponential probability, and there are exponentially many coefficients.
If you take exponentially many samples, it would work, of course.
No, polynomial many samples, but the error in approximating every Fourier coefficient is exponential in the number of samples by the Chernow bound.
No. The error is not the probability of having an error is exponentially small. But the error is
Well,
not.
I mean, the probability that your approximation of
Is
the
bad.
coefficient will be bad is exponentially small. Well, it depends how bad you want, but I don't know if it's some constant or something.
Sorry, is it a Bernoulli distribution when you approximate the expectation of monomial?
So if you assume that the D is uniform, then the D is uniform.
No, but you need to add modulo 2, that's the problem. And then indeed, like Viali says, it will be corrupted because if you're just one off, you get the opposite answer.
Yeah.
Now, if we have if we have parity, then one coefficient will be one big and other will be small. So it's for parity, it should work very nicely.
No, but
Well,
Fourier,
not sure.
so let me remind, Fourier coefficient. So you take uniform distribution and you check the parity. So how to compute them? You need to take parity somewhere, right?
You just multiply it by the if you assume that there are 1 and minus 1s, you multiply it by the monomial and then compute the integral. So you just compare it with the, in other words, you compare the function with the parity of some variables and see how close it to the parity of some variables.
Yes, but
Well, yeah, it's but the point is it's just some expectation. The weighted sum.
Okay,
But
I'm
not
sorry,
model.
but I should go out. Thank you for your
Yeah.
talk.
Yeah, okay.
yeah.
So
Okay.
no, it's strange. It's strange that it would be instead of proving that some natural algorithms work correctly, you prove some quite complicated artificial algorithms to be good. It's a bit somehow strange, but maybe it's just how things are in this domain. I don't know, but
Well, everything is natural here. Well, I mean, what I was saying here.
no, but imagine if you have practical thing, if you have just a small training set that want to learn the decision tree, you will not do what you are saying to do. You will just look on the values and try to guess which variable should be asked first. I believe.
Okay, yeah. I mean, the difference is that if I want, it's natural if I want to prove something. If not, maybe not.
Yeah. So if you look for a proof, then this proof is for some natural
So-
algorithm. But if you just look for an algorithm, it's of kind of practical prediction problem, you will do something different. It's strange. But
Yeah, in theory it's the same, but in practice, the theory. Okay, so
yeah.
theory and practice is the same in theory, but not in practice. So, yeah.
Mm,
Не скажу за практику.
yeah.
Вот.
But is
Okay.
the results when you prove the correctness of some natural algorithm for maybe other classes or for something, that some natural learning algorithm works for some natural or maybe
Okay, is how it's called approximation by polynomial is a natural algorithm. You have a training set and you want to find a polynomial which agrees with it. Like polynomial interpolation, but you try more and more. Like, okay, you want to see like what function you have, what function you can try to fit your data. Well, polynomials, maybe, I don't know, is this a natural choice for you? Are polynomials a natural choice?
no, it depends how you look for them. No. In general, polynomials are okay, but the question is okay, and is there?
I mean, there's the whole area where they have some points and they find this. They have these spines or wherever they try to interpolate, find a small degree polynomial which fits the data, and then they say, okay, then it's and then, for example, this result with DNFs proves that some, if at least some bound, this will be, if you have a small decision tree, then maybe you need a big degree, but not like the max, like degree n over 1 over 3.
Yeah, okay, let me ask finally in a different way. So what I would like to do, there is some, let's have measure of complexity of functions. For example, there are only few significantly non-trivial Fourier coefficients or something like this. And then you have a result that if there is a small decision tree, then, or if there is a small DNF or whatever, then this measure is small. And then you find a learning algorithm which naturally works for all simple function in terms of this measure.
Okay, I understood the definition of a natural algorithm is your algorithm. If
you can think about you will do practically if you want to okay,
they will just do linear regression and all.
Type that's which use some kind of class defined in some, not in terms of circuits, but defines in terms of some property of functions like Fourier coefficients or something like this. And then it's an intermediate step that every simple circuit has this simple or just something like this, no?
Okay, instead of polynomials, you want Fourier coefficients. Well, I guess probably something like that exists, but then I'm not sure. But only you also have to argue that the property of having, like, I don't know, some property of Fourier coefficients is PAC learnable just in the usual sense.
Okay, so maybe then what do we think? Is it maybe next time you will just tell us something in this direction and something? It's what you do with polynomials and how you can learn them and how
Well,
this helps
polynomials, I have to read it first, and I'm not sure that I will be able.
But at least you can use some statement as black box. You said.
I mean, if it's a black box, then there is nothing to explain, more or less.
Okay, you say something very fast, but Okay, let's see what we want to.
Yeah.
So no,
You can also.
I am kind of confused of all this, but this seems to be interesting, and
Well, Sasha, the more talks we have on PAC learning, the more and more you are confused. So maybe we should stop at some point.
before it gets too complicated.
Yeah. And
Before
have
it starts,
some other topic.
yeah, before it starts contaminating areas outside.
What?
No, PAC learning.
Before confusion starts contaminating areas outside PAC learning.
But actually, maybe I have a very special request. There is something in learning, I don't know, PAC learning or non-PAC learning or whatever, which is called win now, some algorithm. And this algorithm was applied to prove something about Kolmogorov complexity. So maybe you can explain this.
I don't know it. So maybe I don't know.
But
Bruno.
just no, I can even, it's easy to find this paper, and I even once I think I tried to read it in some formal and I checked something formally, but I didn't really understood why it's happening and how it's happening. So
Okay, just send it to me, and I don't know. I can tell in a few days whether I will be able.
Paper, and then tell you whether you can explain what is inside or not. Okay.
Excuse me, how is it called again?
It's win now. W-E. I think I can just I can send the reference to the paper and that in chat, and the reference is here.
Bruno has already. Right. Oh. Okay.
No, Bruno wrote just the word win now, and this is what the search gives you from.
Okay, I see. Thanks.
Yeah, maybe then you will also look at the paper, and together with Sasha, you can provide some explanation. You see, it's not that long, or maybe there is a full version somewhere, but it's also not that. Something is proven here about reducibility of Kolmogorov random string. Okay, just please look on this, and then we can maybe we can have this even next time. Okay. So Sasha disappeared. So let's decide that he will give a talk next time about the PAC learning and win now, and see what happens.
Okay.
Yeah.
Goodbye.
Goodbye.
Yeah, thanks. No, we want to say thanks to Sasha, but it's not possible.
Yes.